Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a question that sounds almost impossible at first. Is there something in our universe that seems to move faster than light? Before you settle in completely, I gently invite you, only if you truly enjoy these slow, thoughtful explorations, to like this video and subscribe to the channel, and when you're ready, feel free to leave a comment sharing where in the world you're listening from and what time it is for you right now. It's always a quiet joy to see all the different corners of the planet where these conversations drift through the night. Now you might want to dim the lights a little, maybe let a fan hum softly in the background, or simply close your eyes and rest them. And if your mind wanders as we go along, that's perfectly fine. You can always drift back in whenever you like. We'll still be here, calmly unfolding the story. Tonight, we are not rushing toward answers. We are walking, slowly, through the history of an idea that made some of the greatest physicists deeply uncomfortable. An idea that seemed to threaten the most sacred rule of modern physics, that nothing, absolutely nothing, can outrun light itself. And yet, when scientists looked closely, the universe whispered something stranger, something subtle, something that looks, from a certain angle, like influence without travel. And so, with no urgency at all, let's begin. There is something deeply comforting about the way we expect the world to work. When you flip a light switch, the room brightens. When you let go of a cup, it falls. When you speak, the sound travels outward, reaching nearby ears before distant ones. Causes come first, effects follow after, and there is always a sense of distance being crossed step by step. This expectation is not just a habit of thought, it is the quiet backbone of how we make sense of reality. Imagine standing beside a calm lake at dusk. You toss a small stone into the water and ripples spread outward in widening circles. The disturbance does not appear everywhere at once. It moves steadily, touching one place after another. Even without knowing any physics, you would be surprised if the far shore began to ripple before the stone touched the surface near your feet. In our everyday lives, influence feels local. It travels. It takes time. For centuries, physics seemed to agree. The world was understood as a collection of objects nudging, pulling, and pushing one another through space. Even forces that acted invisibly, like magnetism or gravity, were imagined as stretching across distance in a way that felt continuous, like an unseen thread being tugged. And yet, hidden inside this comfort was a quiet tension. Long before modern physics, people wondered whether influence truly needed time to travel. If the sun were to vanish, not dim or fade, but disappear entirely, when would Earth notice? Intuition might whisper, immediately. After all, if gravity holds us in orbit, shouldn't its absence be felt at once? For a long time, classical physics seemed to agree with that intuition. In the old picture, gravity acted instantly, no matter how far apart two objects were. The pull of the sun reached Earth without delay. Cause and effect, strangely, appeared to be glued together across vast distances. Even the architect of this idea felt uneasy about it. Isaac Newton himself admitted that the notion of one object influencing another instantly across empty space felt absurd. He used that word, absurd, not casually but thoughtfully. Something about it seemed wrong, even if the equations worked. That unease would sit quietly for centuries waiting. The problem with instant influence is not just philosophical discomfort. It becomes dangerous once we realize that time itself is not as universal as it feels. Different observers, moving at different speeds, do not always agree on when events happen. Two flashes of light that seem simultaneous to one observer may appear in sequence to another who is moving past. This is not a trick or an illusion. It is a basic feature of how time works. Now imagine combining that strange flexibility of time with instant action at a distance. If influence were truly instantaneous, one observer might see a cause happen before an effect, while another observer could see the effect come first. Cause and consequence could swap places depending on who was watching. The idea of a stable story, of what happened and why, would begin to unravel. This is why modern physics holds so tightly to speed limits. A universal maximum speed does more than slow things down. It protects causality. It ensures that all observers, no matter how they move, can still agree on the basic order of events. Something happens, and only afterward does its influence arrive elsewhere. When this idea finally crystallized in the early 20th century, it reshaped physics completely. Forces were no longer thought of as instant pulls across emptiness. Instead, changes spread locally, from place to place, like ripples in that quiet lake. Even gravity, once the most mysterious of forces, was reimagined as gentle distortions in space and time that travel outward at a finite pace. If the sun were to vanish, Earth would continue in its orbit for a short while, unaware. Only after about 8 minutes, the time it takes light to cross the distance between them, would the message arrive. The story would unfold in the same order for everyone. First the sun disappears, then Earth responds. By the time this picture settled into place, physics seemed safe again. Every influence had a speed. Every cause waited its turn. The universe respected its own delays, and for a brief moment in history it seemed that nothing could possibly outrun light. But as we will soon see, this sense of safety did not last. Quietly, almost politely, a new theory began to suggest that some connections in nature do not behave like ripples at all. They do not travel. They simply are. And when we look at them closely, they force us to question whether the comfort of cause and effect was ever as solid as it felt. For now, though, we can rest with the familiar idea that speed limits are not obstacles. They are the gentle rules that keep the universe's story from tearing itself apart. The sense of comfort we ended with last time, that causes wait their turn, that influences move patiently through space, feels so natural that it is easy to forget how fragile that idea once was. Before modern physics learned to insist on speed limits, the universe was described in a far stranger way, one that worked beautifully on paper, but left an uneasy feeling in the minds of those who thought about it too carefully. To see this, we need to drift back to a time when gravity was understood very differently. In the classical picture, gravity did not travel. It did not ripple. It didn't arrive late. Instead, it simply acted. If two objects had mass, they pulled on one another immediately, no matter how far apart they were. The distance between them mattered for the strength of the pull, but not for its timing. In this view, the sun did not send gravity outward toward the Earth. The Earth was simply being pulled, continuously, as if connected by an invisible, rigid thread that stretched across empty space. Tug one end, and the other end responded at once. At first glance, this might not seem so strange. After all, gravity does not feel like sound or light. You do not hear it approaching. You do not see it arrive. It is just there, holding planets in their paths and keeping your feet pressed gently against the ground. But if you pause and picture it more carefully, the strangeness begins to show. Imagine the universe as a vast, silent stage. Somewhere far away, an object changes. Perhaps it moves, or vanishes, or explodes. In the classical view, that change would be felt everywhere else instantly. There would be no waiting, no gradual spreading, no sense of motion at all. The effect would simply appear, fully formed across unimaginable distances. Even the man who gave us this law of gravity found the idea unsettling. He admitted openly that the notion of one object influencing another across empty space, without anything mediating the interaction, seemed deeply implausible. He did not claim to understand how gravity worked at a fundamental level. He only knew that the mathematical description matched what people observed, and for a long time, that was enough. Classical physics had a certain confidence to it. If a theory made accurate predictions, questions about its deeper meaning could be set aside. Gravity, despite its odd immediacy, allowed astronomers to chart the motion of planets with remarkable precision. The heavens moved as expected. The equations held. Still, the discomfort lingered quietly in the background, like a loose floorboard no one wanted to step on. The real trouble began when physicists realized that time itself was not as simple as it had once seemed. In everyday life, we assume that there is a single, universal now. Two events either happen at the same time or one happens before the other, and everyone agrees on the order. But this assumption turns out to be a convenience, not a law of nature. Once it became clear that observers moving at different speeds can disagree about the timing of events, the idea of instant influence took on a darker tone. If gravity acted immediately, then its effects could be reordered by motion. What looked like a cause followed by an effect in one frame of reference could appear reversed in another. This is not just a technical curiosity. It strikes at the heart of what it means for the universe to make sense. Consider again the thought of the sun disappearing. In the classical picture, the Earth would feel the loss of gravity at the same moment the sun vanished. But because different observers disagree about what the same moment means, some observers could describe a situation in which the Earth begins to drift away before the sun is gone. The effect would appear to precede the cause. That kind of story does not merely feel strange, it feels impossible. If causes and effects can trade places depending on who is watching, then the universe loses its narrative consistency. Events no longer form a reliable chain. Explanations begin to collapse under their own weight. This realization transformed the discomfort surrounding instant gravity into an outright crisis. Something had to give. Either time behaved very differently than anyone expected, or gravity could not be instant after all. The solution, when it finally came, was both radical and calming. Instead of imagining gravity as a force that leaps across space, it was reimagined as a gentle reshaping of the very stage on which everything moves. Space and time themselves could bend, curve, and respond to mass and energy. Changes in this curvature would not appear everywhere at once. They would spread outward, region by region, at a finite pace. In this new picture, gravity became local. A change here affected the immediate surroundings first, and only later influenced distant regions. The universe regained its sense of order. All observers, regardless of how they moved, could agree on the basic sequence. First the cause, then the effect. This shift did more than fix gravity. It established a principle that would come to define modern physics. No influence, no matter how subtle or invisible, should outrun light. The speed of light was not merely a property of illumination. It was a kind of cosmic speed limit, woven into the structure of reality itself. By the time this idea settled in, physics seemed to have learned its lesson. Instant action at a distance was not just uncomfortable, it was incompatible with a universe where time depends on motion. Locality, the idea that influences spread step by step through space, became a guiding rule. And for a while it seemed that the problem had been solved once and for all. Gravity, the most obvious offender, had been tamed. Forces behaved themselves, causes waited their turn. The universe, though strange, felt internally consistent again. But beneath this restored calm, another theory was quietly taking shape. It did not announce itself with paradoxes right away. In fact, it worked astonishingly well, predicting experimental results with unmatched precision. Yet hidden within its rules was a mechanism that looked eerily familiar. A mechanism that, like Newton's gravity before it, seemed to allow influence without travel. At first, few people noticed, and those who did were often told that the discomfort was philosophical, not physical. The equations worked. The predictions were right. Why worry? As we'll soon see, one physicist refused to let that question go, and his unease would eventually lead us back to a universe that once again appears to whisper across distance, faster than any signal should be allowed to move. By the time gravity had been reimagined as something local, spreading gently through space and time rather than leaping across it, physics seemed to have found its footing again. The universe felt coherent. Causes came first. Effects followed. And the unsettling thought of instant influence faded into the background, like a bad dream that dissolves after waking. To understand why this felt so satisfying, it helps to slow down and picture what local really means in this context. Imagine a vast field of tall grass on a calm morning. If a breeze passes through, the grass does not all bend at once. It leans here first, then there, a visible wave rolling across the field. Even if the wind is strong, it still has a direction and a pace. You can watch it move. This is what locality feels like. Change happens somewhere, and then it spreads. When gravity was reinterpreted as a bending of space and time itself, it took on this same character. A massive object did not shout instructions across the universe. Instead, it shaped its immediate surroundings. Those surroundings influenced their neighbours and so on, until the message eventually reached distant regions. Nothing jumped ahead. Nothing arrived before it should. This was more than a technical fix. It was a deep reassurance that the universe respects narrative order. In a world governed by locality, stories make sense. A planet moves because the shape of space around it guides its path. A clock ticks slower because the flow of time is gently altered nearby. Every effect can be traced back step by step through a chain of influences that never outruns the fastest messenger in nature. That messenger, of course, is light. Light's speed is not just about how quickly brightness reaches your eyes. It is the maximum pace at which information of any kind can move. It is the universe's way of saying, no matter how strange things get, there will always be time between cause and effect. This delay is not an inconvenience. It is a safeguard. Without it, different observers could tell radically different stories about the same events. One person might say that a cause came first. Another, moving at a different speed, might insist that the effect happened earlier. Reality itself would lose its shared timeline. But with a universal speed limit in place, something remarkable happens. Observers may disagree about how long a delay lasts, but they agree on the order. The cause always comes before the effect. The story remains intact. This is why the speed of light holds such a special place in modern physics. It is not merely fast, it is foundational. Once this idea settled in, it reshaped how physicists thought about everything. Forces could no longer act instantly. Signals had to travel. Even time itself was woven into this structure, stretching and compressing as needed, but never allowing influence to cheat the cue. For a while, it seemed that the universe had revealed one of its deepest rules, and many physicists felt that the most troubling puzzles were finally behind them. There is a quiet confidence that comes with believing you have identified the boundaries of what is possible. If nothing can outrun light, then paradoxes are kept at bay. Messages cannot arrive before they are sent. Effects cannot precede causes. The universe may be strange, But it is not self-contradictory. This belief became so deeply ingrained that it felt almost sacred. Faster than light was not just unlikely, it was forbidden. And yet, even as this framework solidified, another theory was gaining ground. It did not challenge the speed of light directly. In fact, it seemed perfectly compatible with it, at least on the surface. It made predictions that were stunningly accurate, far beyond anything physics had known before. This new theory was quiet where relativity was bold. It spoke in probabilities rather than certainties. It described waves of possibility instead of definite paths, and it did not announce trouble right away. But hidden within its language was a subtle tension. Unlike gravity, which had been forced to become local to preserve causality, this new theory appeared to describe states that were not confined to any single place. Its fundamental objects were not points or particles in the usual sense. They were descriptions spread across space, like mist filling a room. At first, this did not seem dangerous. After all, probabilities can be spread out without causing trouble. A weather forecast covers a wide region, but it does not imply that rain falls everywhere at once. The problem only emerged when those probabilities were confronted by measurement. When something is observed, something changes. Possibilities give way to outcomes. And in the theory that was taking shape, this change did not appear to respect the same local, ripple-like structure that gravity had been forced to adopt. Where relativity insisted on patience, this new framework seemed to permit abrupt decisions. For some physicists, this was not alarming. The theory worked. It predicted results with astonishing precision. Why worry about what happened behind the scenes? For others, the unease returned. If gravity had once been suspicious because it acted instantly, why should we be comfortable with any process that appeared to do the same? Had physics truly escaped action at a distance, or had it merely disguised it? These questions did not yet have sharp edges. They hovered quietly, like distant thunder, but they were enough to trouble a physicist who cared deeply about coherence and clarity. The universe, after all, had already taught one lesson. Instant influence leads to paradox. Locality preserves order. And any theory that violates this spirit, even subtly, risks reopening wounds that were thought to have healed. As we drift forward, we will meet the moment when this tension could no longer be ignored, when a simple question about a single particle forced physicists to confront the possibility that locality, so carefully restored, might once again be slipping through their fingers. For now, though, we can rest in the calm of a universe that learned to respect its own speed limit. A universe where change travels gently, never rushing ahead of itself. A universe that seems, at least for a moment, at peace with the flow of cause and effect. With the idea of locality firmly in place, physics entered the 20th century with a quiet sense of confidence. The universe had rules. Those rules protected cause and effect, and nothing, it seemed, could outrun light. Then, almost without warning, a new theory began to describe the world in a language that felt entirely different. Instead of clear paths and predictable motions, it spoke of possibilities. Instead of particles behaving like tiny solid beads, it suggested something more diffuse, more elusive. Objects were no longer always somewhere. In a very real sense, they could be everywhere they were allowed to be. To understand this shift, it helps to imagine something familiar. Picture a single drop of perfume released into a still room. At first, it is concentrated near the bottle, but as time passes, the scent spreads. It drifts into corners, seeps under doors, and fills the space evenly. You cannot point to a single location and say the perfume is only here. Instead, it exists as a soft cloud, more intense in some regions, fainter in others. Quantum mechanics asked us to think about particles in a similar way. When physicists described a single electron, they no longer spoke only of a precise location moving along a track. Instead, they described a wave of possibility, a mathematical object that spread through space. This wave did not represent ignorance, as though the electron had a secret location we simply did not know. According to the theory, the electron genuinely occupied all of these possibilities at once. Where the wave was stronger, the electron was more likely to appear if measured. Where it was weaker, appearance was less likely. But until a measurement occurred, the theory refused to say that the electron was actually anywhere in particular. This idea was unsettling, but it was also extraordinarily successful. Time and again, experiments confirmed the predictions. When electrons were fired one at a time toward a detection screen, they did not land randomly. Over many trials, a pattern emerged, matching the gentle hills and valleys of the probability wave with uncanny accuracy. The universe, it seemed, was playing a subtle statistical game, and winning. At first, there was no obvious threat to locality here. A spread-out wave of possibility does not, by itself, cause trouble. After all, weather forecasts cover entire regions, but storms still move locally. Probabilities can be broad without implying that anything physically jumps across space. The discomfort only emerged when physicists asked a simple, almost innocent question. What happens when we actually look? Imagine again that electron drifting as a mist of possibility toward a screen. According to the theory, its wave extends across the entire surface. The electron is not heading toward one specific point. It is, in a sense, heading toward all of them. Then, suddenly there is a flash. A single spot lights up on the detector. The electron has appeared. This moment, the act of measurement, is where the calm story begins to tremble. The theory tells us that once the electron is detected at one location, it will not appear anywhere else. There is only one electron after all, it cannot be found twice. And so the wave of possibility must change. The probability of finding the electron at the observed spot becomes certain, while the probability everywhere else drops to nothing. The mist clears, everywhere. Not gradually, not ripple by ripple, but all at once. This is not a detail buried deep in equations. It is central to how the theory works. Without this sudden update, the predictions would fail. Detectors would occasionally click twice. Conservation rules would be violated. The tidy match between theory and experiment would fall apart. And yet, if you pause and reflect on what this implies, the old unease returns. The moment the electron is detected here, the description of the electron changes everywhere else, instantly. No matter how far away those regions are, the update does not wait, it does not propagate, it simply happens. For some physicists, this was not alarming. They viewed the wave of possibility as a bookkeeping tool, a way to organize predictions, not a physical object that needed to obey rules about motion and speed. If the wave was not real, then its sudden change was not a physical influence travelling through space. It was just an update in our description. But others were not satisfied with that answer. If the wave is merely a tool, why does it work so reliably? Why does it predict experimental outcomes with such astonishing precision? And if it is not real, what is the electron doing before we look? These questions were not idle philosophy. They cut directly into the meaning of the theory. One physicist in particular found this deeply troubling. He had already spent years reshaping physics to eliminate instant action at a distance. He had learned the hard way that allowing influences to outrun light leads to paradox and confusion. And now, here was a theory that seemed to reintroduce something uncomfortably similar, not as a force, but as a sudden global change in description. From his perspective, it looked like a step backward. The measurement here, he argued, must somehow affect the description of the particle over there. Even if no signal could be sent, even if no message could be encoded, the theory still seemed to require a kind of instantaneous coordination across space. This clashed with the spirit of locality that relativity had so carefully restored. To him, this was not a minor technical quirk. It was a sign that something fundamental was missing. Perhaps the wave of possibility was not the whole story. Perhaps there were deeper variables hidden beneath the surface, quietly determining outcomes in a local way. Not everyone agreed. Many were content to accept the wave as the final word. The theory worked, and that was enough. Questions about what happened when no one was looking were dismissed as meaningless or unproductive. But the seed of doubt had been planted. The universe once again appeared to be flirting with influence without travel. And if history had taught physics anything, it was that such flirtations rarely ended quietly. As we continue, we will see how this unease grew from a single particle to pairs of particles linked across space, how a subtle discomfort became a sharp dilemma, and how a debate about what it means to measure something would eventually force physicists to confront the possibility that locality itself was in trouble once more. For now, we can sit with the image of a wave that is everywhere, calm, mathematical, and seemingly innocent. A wave that waits patiently for observation, and when observed, changes the story of the universe in a way that no ripple ever could. Up to this point, the story of quantum mechanics has felt strange, but not dangerous. A particle described as a mist of possibilities may stretch our imagination, yet it does not obviously threaten the careful structure physics had built around locality and speed limits. A cloud can be wide without moving quickly. Uncertainty can exist without causing paradox. The real trouble begins at the moment that mist disappears. To understand why, let's return to the image of the electron drifting toward a detection screen. Before anything is observed, the theory asks us to think of the electron not as a tiny object flying along a path, but as a spread-out description, a pattern of likelihoods filling the space in front of the screen. This pattern evolves gently and predictably, like a wave rolling forward. Nothing here seems to violate the universe's patience. Then comes the act of measurement. A single point on the screen lights up. One small region responds, and the rest do not. The electron is found. The story appears to resolve itself cleanly, but the theory demands something more than just a local event. The description of the electron must be updated everywhere else as well. The possibility of finding the electron at any other point must instantly disappear. Not later. Not gradually. Immediately. This sudden change is often described using a single word: collapse. The wave of possibility collapses from a wide, gentle fog into a sharp, localized outcome. Before the measurement, many futures coexist. After the measurement, only one remains. At first, collapse sounds like a technical detail, something that happens inside the mathematics. But when you pause and picture it, the implications are hard to ignore. The electron might have been spread across a vast region of space. Parts of its description could have extended to places unimaginably far away. Yet the moment it is detected here, the description everywhere else changes at once. There is no waiting period, no ripple travelling outward. The update does not respect distance. This is where the old discomfort returns, now sharper and more focused. In the case of gravity, instant influence was troubling because it conflicted with relativity's flexible notion of time. Collapse seems to do something similar, but in a more subtle way. It does not transmit energy or matter. It does not allow messages to be sent, and yet it appears to coordinate outcomes across space without delay. For some physicists, this was not a problem at all. They argued that collapse is not a physical process. It does not represent something happening in the world, but rather something happening in our description of the world. When we gain information, we update our expectations. The sudden change reflects knowledge, not influence. In this view, the wave of possibility is like a weather forecast. When new data arrives, the forecast can change everywhere at once. That does not mean the weather itself changed instantly. Only our understanding did. This perspective offered comfort. It allowed physicists to preserve locality by declaring collapse to be an abstract bookkeeping step rather than a real event. But not everyone was satisfied with this move. If collapse is merely about knowledge, then what is the wave describing before we look? Is it just a tool for prediction? Or is it something that corresponds, however imperfectly, to reality itself? And if it is only a tool, why does it behave so consistently, so reliably, as if it were tracking something real? These questions cut deeply into the meaning of the theory. The trouble is that quantum mechanics does not merely say, we don't know where the electron is before measurement. It says that the electron does not have a definite location at all. The wave is not a veil over hidden facts. It is, according to the theory, the most complete description available. If that is true, then collapse is not just a change in knowledge, it is a change in what exists. And that change appears to happen everywhere at once. This is why measurement became the central mystery. Not probability, not randomness, measurement. Something special happens when a quantum system interacts with the world in a way that produces a definite outcome. The theory treats this moment differently from all other processes. Smooth evolution gives way to abrupt decision. For one particular physicist, this asymmetry was deeply unsettling. He had already spent years eliminating instant action, at a distance from physics. He had learned to distrust any theory that relied on unexplained leaps across space. And now, quantum mechanics seemed to demand exactly that, not as an optional interpretation, but as a core feature of how predictions were made. From his perspective, collapse looked like a step backward. Gravity had been forced to abandon its instantaneous behavior to preserve causality. Why should quantum mechanics be allowed to keep something so similar, merely hidden behind mathematical language? To him, this suggested that the wave of possibility was incomplete. Perhaps it was a useful approximation, but not the final story. Perhaps there were deeper elements, variables not yet seen, that quietly determined outcomes in advance, allowing the world to remain local even if our descriptions did not. This was not a rejection of quantum mechanics' success. It was a demand for clarity. The theory worked remarkably well, but its meaning felt unfinished. Measurements seemed to play an outsized role, as if reality itself waited for an observer's glance before deciding what it was. Many physicists were willing to accept this oddity. They argued that physics should focus on predictions, not metaphysical discomfort. If the theory told you what would happen in the lab, that was enough. Asking what an electron really does when no one is watching was, in their view, a meaningless question. But to those who cared deeply about coherence, this answer rang hollow. Physics had once been content with instant gravity because it worked, and yet that contentment had eventually given way to revolution. The discomfort had mattered. It had pointed to something deeper. Collapse felt like the same kind of warning sign. If the universe truly allows descriptions to change everywhere at once, then locality, the idea that distant regions are independent unless connected by signals, is in trouble. Even if no message can be sent, even if no paradox arises, the spirit of relativity seems to be violated. The fog of possibility, when it vanishes, does not do so gently. As we move forward, this tension will grow sharper. The mystery of collapse will no longer involve a single particle. but pairs of particles linked in ways that seem impossible to explain without either instant influence or hidden coordination. For now, we can rest with the unsettling image at the heart of quantum mechanics. A universe that drifts calmly in probabilities until observation arrives and the fog clears everywhere at once. By the time the mystery of collapse had fully settled into the foundations of quantum mechanics, physicists found themselves standing at an unexpected crossroads. The equations worked, the predictions were astonishingly accurate, and yet the story those equations seemed to tell about reality felt incomplete, even contradictory. Something had to give. At this point, the debate was no longer about experiments or measurements on screens. It had become a question about what physics was supposed to be. Was it a description of the world as it exists, or merely a set of rules for predicting what we will observe? The answer to that question led down two very different paths. One response was to accept collapse exactly as it appeared, no matter how strange it seemed. According to this view, the wave of possibility truly was the most complete description available. Before measurement, reality itself was not settled. It existed as a collection of potential outcomes, none more real than the others. When a measurement occurred, the universe made a choice. This choice did not unfold gradually. It did not respect distance. It simply happened. Supporters of this view argued that it was a mistake to demand a deeper explanation. Physics, they said, is not obligated to tell us what the world is like when we are not looking. Its task is to connect preparations to outcomes, questions to answers, and in that task, quantum mechanics excelled. If collapse appeared non-local, so be it. Nature was under no obligation to match our intuitions. This perspective offered a kind of peace. By refusing to ask certain questions, it avoided contradictions. The cost was philosophical discomfort, but the reward was practical success. Experiments could be designed, technologies could be built, the theory delivered. The other response was very different. Some physicists could not accept that the universe waited for observation to decide what existed. They could not accept that reality itself depended on acts of measurement, especially when those acts appeared to rearrange descriptions across vast distances in no time at all. To them, collapse felt less like a feature and more like a warning. They suspected that the wave of possibility was not the whole story. Perhaps it was an incomplete description, useful but not fundamental. Perhaps beneath it lay additional details, quietly determining outcomes in advance, restoring locality and continuity to the world. In this picture, the electron does not drift in a fog of undecided futures. It follows a definite course, guided by information we do not yet have access to. Measurement does not create reality, it reveals it. This idea was deeply appealing. It preserved the familiar structure of cause and effect. It allowed influences to remain local, and it removed the special, almost magical status of measurement. But there was a problem. If such hidden details existed, they would have to be coordinated with exquisite precision. They would need to ensure that quantum predictions were reproduced exactly, even in the most delicate experiments. And they would need to do so without allowing signals to travel faster than light. This was not obviously impossible. In fact, it felt quite reasonable. After all, physics had been surprised before by deeper layers beneath successful theories. Classical mechanics had once seemed complete. Later, it was revealed as an approximation. Why not quantum mechanics as well? And yet the tension remained. Both paths had costs. Accepting collapse meant living with a universe that seemed to violate locality, even if it carefully avoided outright paradox. Rejecting collapse meant committing to unseen structures and mechanisms that had not yet revealed themselves experimentally. This was not a technical disagreement, it was a philosophical fork in the road. What made the situation especially uneasy was that, at this stage, there was no way to decide between the two options using experiments. Both approaches made exactly the same predictions for all known tests. No matter how clever the setup, the outcomes would agree. To many physicists, this made the debate feel sterile. If no experiment could distinguish the options, why spend time arguing about them? Why not pick the interpretation that worked and move on? This attitude quietly became dominant. Students were taught how to calculate outcomes, not how to worry about what they meant. The deeper questions were treated as distractions better left to philosophers, but the discomfort did not disappear. It merely went underground. Those who worried about locality noticed something important. The tension introduced by collapse was not an isolated quirk. It echoed the earlier problem with gravity. In both cases, a successful theory seemed to rely on influence without travel. In both cases, the discomfort pointed toward the possibility that the theory was incomplete. History had shown that such discomfort could be productive. The challenge, then, was to find a way to sharpen the question, to move beyond thought experiments and philosophical unease, to design a situation in which the two paths, accepting non-local collapse or insisting on a deeper local description, would finally lead to different predictions. At the time, this seemed unlikely. The wave of possibility and the hidden details approach appeared experimentally indistinguishable. Both could explain everything that had been observed, and so the debate simmered quietly for years. Yet beneath the surface, the ingredients for a breakthrough were already present. The idea of linking particles together in shared states, the recognition that measurement choices could matter, the realization that locality itself might be testable, not as a vague principle, but as a concrete assumption. All that was missing was someone willing to revisit the problem with fresh eyes, someone willing to take the old discomfort seriously, someone who would ask not how to interpret quantum mechanics, but whether the universe itself could be coaxed into revealing which path it had taken. As we drift onward, we will meet that person, and with him, the moment when philosophy finally crossed the threshold into experiment, forcing nature to answer a question it had avoided for decades. For now, we can rest at the fork in the road, aware that physics had reached a point where calculation alone was no longer enough. The universe was working, but its meaning remained unresolved. Up to this point, the tension in quantum mechanics has revolved around a single particle, one electron, one wave of possibility, one moment of measurement where uncertainty gives way to outcome. That alone was troubling enough, but the story does not stop there. In fact, it deepens. Imagine now that instead of one particle, we have two. They are created together in a single event, like two notes struck at the same moment on a piano. From the very beginning, their properties are linked, not vaguely correlated, but precisely balanced, as though nature itself were keeping a careful ledger. To make this feel concrete, let's talk about a simple property: orientation. You can think of it as a tiny arrow carried by each particle, pointing in some direction. For everyday object, orientation is straightforward. A compass needle points north or south. A spinning top tilts one way or another. For these particles, orientation behaves differently. Before we look, neither particle's arrow points in any single direction. Instead, each exists in a state of possibility, able to point one way or another depending on how it is examined. What matters most is not the direction itself, but the relationship between the two arrows. They are born together in a perfectly balanced state. Whatever one arrow eventually turns out to be, the other must be opposite. If one points up, the other points down. If one points left, the other points right. The total balance is preserved. At first, this seems harmless. Conservation rules like this are familiar. If you and a friend start with equal amounts of money and one of you gains $1, the other must lose one. Nothing mysterious there. The strangeness appears when the two particles are separated. Imagine sending one particle far away, across a room, across a city, across a planet. The other stays with you. Distance, in classical thinking, weakens relationships. Signals fade. Connections loosen. But in this case, the link remains perfect. You decide to examine the particle near you. You choose a particular way of looking at its orientation, a specific direction along which to ask your question. When you do, the particle responds. Its arrow is found pointing one way rather than the other. At that exact moment, the distant particle's orientation is fixed as well. Not eventually, not after a delay, immediately. If you were to examine it in the same way, you would find the opposite result with complete certainty. This is what physicists call entanglement. The two particles do not merely share a history, they share a description. Their states are intertwined in such a way that neither can be fully described without reference to the other, no matter how far apart they are. At first glance, this looks like instant communication. How else could the distant particle know how to respond? But the situation is subtler than that. When you examine your particle, you do not get to choose the result. You do not decide whether it points one way or the other. The outcome is random. Half the time it goes one way, half the time the opposite. There is no message encoded in your measurement, and yet the correlation is perfect. If someone far away examines their particle using the same method, their result will always match yours in the appropriate opposite way. The connection is absolute, even though neither side can control what happens. This combination, randomness locally, certainty jointly, is what makes entanglement so strange. To help visualize this, imagine two sealed envelopes prepared together. Inside one is a card marked up, inside the other a card marked down. The envelopes are mixed, sealed, and sent to opposite ends of the world. When you open yours and see up, you instantly know that the other contains down. There is nothing mysterious about this example. The information was placed in the envelopes at the beginning. The envelopes are merely revealing what was already there. The unsettling part of entanglement is that quantum mechanics insists this is not what is happening. Before measurement, there is no card in either envelope. The particles are not secretly carrying fixed answers. Their orientations are not set in advance. They exist in a shared state of possibility that only resolves when someone looks. This is where the earlier discomfort about collapse returns, now amplified. When you measure your particle, its state becomes definite. At the same time, the description of the distant particle becomes definite as well. The wave of possibility connecting them adjusts instantly, regardless of the distance between them. It feels as though the act of looking here reaches out and rearranges reality there. For those who were already uneasy about collapse in single-particle systems, this was deeply alarming. The non-local character of the theory was no longer confined to abstract probability waves. It appeared directly in the relationships between separate objects in space. If this was truly how nature worked, then locality, the principle that distant things cannot affect one another without intermediaries, seemed to be in serious trouble. And so the old question returned, now sharper than ever. Is this instant coordination real, or is it only an illusion created by an incomplete description? There was a way out that felt natural and reassuring. Perhaps the particles do carry hidden instructions after all. Perhaps, when they're created together, they agree on a plan. They decide in advance how they will respond to any possible way of being examined. When separated, they simply follow the plan. In this picture, nothing travels faster than light. There is no instant influence. The envelopes really do contain cards. We just didn't know which until we opened them. This idea preserved locality. It restored a sense of independence between distant regions. It made the universe feel sensible again, and for a time, it seemed entirely plausible. After all, quantum mechanics already allowed for probabilities. Why not imagine that beneath those probabilities lay definite but hidden facts? Facts that ensured the perfect correlations without requiring spooky coordination across space. This was the heart of the challenge that emerged from entanglement. Either the universe allows connections that ignore distance, or it contains hidden structures that we have not yet uncovered. At this stage, both possibilities were open. Both explained everything that had been observed. The tension had grown, but it was still unresolved. As we continue, this quiet standoff will harden into a sharp dilemma. The envelope analogy will be pushed further. The idea of prearranged plans will be tested in situations where intuition begins to fail. For now, we can rest with the image of two particles drifting apart, carrying a shared story that space itself seems unable to dilute. A story that waits, patiently, for the moment when someone finally asks the universe the right question. Up to this point, the tension in quantum mechanics has revolved around a single particle. One electron, one wave of possibility, one moment of measurement where uncertainty gives way to outcome. That alone was troubling enough. But the story does not stop there. In fact, it deepens. Imagine now that instead of one particle, we have two. They're created together in a single event, like two notes struck at the same moment on a piano. From the very beginning, their properties are linked, not vaguely correlated, but precisely balanced, as though nature itself were keeping a careful ledger. To make this feel concrete, let's talk about a simple property: orientation. You can think of it as a tiny arrow carried by each particle, pointing in some direction. For everyday objects, orientation is straightforward. A compass needle points north or south. A spinning top tilts one way or another. For these particles, orientation behaves differently. Before we look, neither particle's arrow points in any single direction. Instead, each exists in a state of possibility, able to point one way or another depending on how it is examined. What matters most is not the direction itself, but the relationship between the two arrows. They are born together in a perfectly balanced state. Whatever one arrow eventually turns out to be, the other must be opposite. If one points up, the other points down. If one points left, the other points right. The total balance is preserved. At first, this seems harmless. Conservation rules like this are familiar. If you and a friend start with equal amounts of money and one of you gains $1, the other must lose one. Nothing mysterious there. The strangeness appears when the two particles are separated. Imagine sending one particle far away, across a room, across a city, across a planet. The other stays with you. Distance, in classical thinking, weakens relationships. Signals fade, connections loosen. But in this case, the link remains perfect. You decide to examine the particle near you. You choose a particular way of looking at its orientation, a specific direction along which to ask your question. When you do, the particle responds. Its arrow is found pointing one way rather than the other. At that exact moment, the distant particle's orientation is fixed as well. Not eventually, not after a delay, immediately. If you were to examine it in the same way, you would find the opposite result with complete certainty. This is what physicists call entanglement. The two particles do not merely share a history, they share a description. Their states are intertwined in such a way that neither can be fully described without reference to the other, no matter how far apart they are. At first glance, this looks like instant communication. How else could the distant particle know how to respond? But the situation is subtler than that. When you examine your particle, You do not get to choose the result. You do not decide whether it points one way or the other. The outcome is random. Half the time it goes one way, half the time the opposite. There is no message encoded in your measurement, and yet the correlation is perfect. If someone far away examines their particle using the same method, their result will always match yours in the appropriate opposite way. The connection is absolute, even though neither side can control what happens. This combination, randomness locally, certainty jointly, is what makes entanglement so strange. To help visualize this, imagine two sealed envelopes prepared together. Inside one is a card marked up. Inside the other, a card marked down. The envelopes are mixed, sealed, and sent to opposite ends of the world. When you open yours and see up, you instantly know that the other contains down. There is nothing mysterious about this example. The information was placed in the envelopes at the beginning. The envelopes are merely revealing what was already there. The unsettling part of entanglement is that quantum mechanics insists this is not what is happening. Before measurement, there is no card in either envelope. The particles are not secretly carrying fixed answers. Their orientations are not set in advance. They exist in a shared state of possibility that only resolves when someone looks. This is where the earlier discomfort about collapse returns, now amplified. When you measure your particle, its state becomes definite. At the same time, the description of the distant particle becomes definite as well. The wave of possibility connecting them adjusts instantly, regardless of the distance between them. It feels as though the act of looking here reaches out and rearranges reality there. For those who were already uneasy about collapse in single particle systems, this was deeply alarming. The non-local character of the theory was no longer confined to abstract probability waves. It appeared directly in the relationships between separate objects in space. If this was truly how nature worked, then locality, the principle that distant things cannot affect one another without intermediaries, seemed to be in serious trouble. And so the old question returned, now sharper than ever. Is this instant coordination real? Or is it only an illusion created by an incomplete description? There was a way out that felt natural and reassuring. Perhaps the particles do carry hidden instructions after all. Perhaps, when they are created together, they agree on a plan. They decide in advance how they will respond to any possible way of being examined. When separated, they simply follow the plan. In this picture, nothing travels faster than light. There is no instant influence. The envelopes really do contain cards. We just didn't know which until we opened them. This idea preserved locality. It restored a sense of independence between distant regions. It made the universe feel sensible again, and for a time it seemed entirely plausible. After all, quantum mechanics already allowed for probabilities. Why not imagine that beneath those probabilities lay definite but hidden facts? Facts that ensured the perfect correlations without requiring spooky coordination across space. This was the heart of the challenge that emerged from entanglement. Either the universe allows connections that ignore distance, or it contains hidden structures that we have not yet uncovered. At this stage, both possibilities were open. Both explained everything that had been observed. The tension had grown, but it was still unresolved. As we continue, this quiet standoff will harden into a sharp dilemma. The envelope analogy will be pushed further. The idea of prearranged plans will be tested in situations where intuition begins to fail. For now, we can rest with the image of two particles drifting apart, carrying a shared story that space itself seems unable to dilute. A story that waits patiently for the moment when someone finally asks the universe the right question. The image of the envelopes is comforting for a reason. It takes something unsettling and translates it into a story we already understand. If answers are placed inside from the beginning, then distance is no threat. Nothing needs to travel, nothing needs to hurry. The universe keeps its secrets neatly packed until the moment they are revealed. This is how we instinctively want the world to work. So when physicists first confronted entanglement, many were drawn to this idea without hesitation. Surely the particles must be carrying instructions. Surely the outcomes are decided early, when the particles are created together, still close enough to whisper to one another without breaking any cosmic speed limits. In this picture, measurement is no longer mysterious. It is simply the opening of an envelope. You open yours and find a result. Somewhere far away, another person opens theirs and finds the matching counterpart. The coordination feels miraculous only because we forgot that the agreement was made in advance. If this were the whole story, the discomfort would dissolve. Collapse would no longer be an abrupt universe-wide update. It would be a local unveiling of facts that were always there. For a while, this explanation seemed not only reasonable, but elegant. It aligned perfectly with the desire for locality. It preserved the idea that distant regions of space are independent unless connected by signals, and it rescued reality from the unsettling notion that observation itself plays a creative role. But there was a subtle problem lurking beneath this calm surface. The envelope story only works if the questions we ask are fixed in advance. Imagine that the envelopes contain cards labelled simply up and down. If you and your distant partner always ask the same question, always open the envelope in the same way, the illusion holds. You will always see perfectly matched results. But quantum experiments allow for something more flexible. You're not limited to one way of examining the particle. You can choose different orientations, different perspectives, different questions to ask, and crucially, you can make this choice at the last moment, after the particles have already parted ways. This freedom changes everything. To see why, imagine expanding the envelope analogy. Instead of a single card, each envelope now contains a small instruction booklet. The booklet tells the particle how to respond to every possible question you might ask. If you check orientation this way, answer up. If you check it another way, answer down. The distant particle carries a matching booklet, carefully coordinated so that the overall balance is always preserved. At first, this still feels manageable. The particles agree on a strategy before separating. They are prepared for every possibility. But as we allow more freedom in the questions, more directions, more ways of looking, the booklets must grow more complex. They must contain a complete plan, mapping every possible choice to a specific outcome. And here is where intuition begins to strain. Quantum mechanics predicts not just perfect agreement when the same question is asked, but very specific patterns of agreement and disagreement when different questions are chosen. The correlations are delicate. They are not all or nothing. They fall into precise proportions. Sometimes the answers match, sometimes they differ, and the frequency of these matches and mismatches follows a pattern that seems simple on the surface, but is remarkably hard to fake. If the envelope explanation is correct, the instruction booklets must reproduce these patterns exactly. They must do so using only pre-arranged information, without knowing in advance which questions will actually be asked. This is where the explanation begins to wobble. No matter how cleverly the instructions are written, they face a constraint. They must commit to answers ahead of time. They cannot adapt on the fly. Once the particles separate, the plan is locked in. Quantum mechanics, however, behaves as though the answers are not locked in at all. The outcomes seem to depend not only on the shared past of the particles, but also on the choices made at the moment of measurement. This does not mean the particles are sending messages. Remember, the outcomes are random locally. There is no way to steer them. But the pattern of correlations appears to reflect the measurement choices in a way that pre-written plans struggle to reproduce. The envelope analogy begins to feel like a cardboard prop. It looks solid until you press on it. Physicists began to realize that if hidden instructions existed, they would have to be extraordinarily sophisticated. They would need to anticipate every possible question and coordinate answers in a way that mimicked the subtle statistical structure of quantum predictions. And yet, even with unlimited ingenuity, something seemed to be missing. The discomfort returned, sharper now. If the particles are truly independent once separated, how can their answers reflect choices made later, far away? If the instruction booklets are fixed, why do the correlations look as though they're responding to the present, not just the past? This is the heart of the puzzle that grew out of entanglement. It is not simply that the particles agree, it is how they agree. The structure of their correlations carries a signature that seems to reach beyond any simple prearranged script. At this stage, the debate was still unresolved. The envelope explanation had not been disproven. It had merely begun to feel strained, like a story that requires too many coincidences to remain believable. What was needed was a way to turn this discomfort into something sharper, something testable. Rather than asking whether hidden instructions were possible in principle, physicists needed to ask a more precise question. Is there any way, no matter how clever, for pre-written answers to reproduce the full pattern of correlations predicted by quantum mechanics? This was not a philosophical question. It was a mathematical one, and it would soon be transformed into an experimental challenge. But before that happened, the universe waited. The envelope stayed sealed. The particles continued to behave exactly as quantum mechanics predicted, and the sense of unease lingered, quietly insisting that something about the story still did not add up. As we drift onward, this gentle tension will crystallize into a clear dividing line, a line that separates what can be explained by hidden agreements from what seems to require something far stranger. For now, we can rest with the image of an envelope that feels reassuring, yet somehow insufficient. A simple story that almost works, but not quite. And in that almost, the universe prepares to reveal one of its most surprising truths. For many years, the unease surrounding quantum mechanics lived in an odd place. It was well known, frequently discussed, and yet rarely acted upon. Students learned how to calculate results with remarkable accuracy. Engineers learned how to turn those calculations into working machines. Meanwhile, the deeper questions, the ones about locality, reality, and what the equations actually meant, were politely set aside. The theory worked, and that, for most people, was enough. But not for everyone. There was a young physicist who came of age long after the initial battles over quantum mechanics had faded from view. By the time he entered the field, the debates between Einstein and Bohr were already treated as historical curiosities, almost philosophical footnotes. The textbooks presented a settled story. Quantum mechanics had won, its critics had been answered, and the remaining puzzles were matters of interpretation rather than substance. Yet as he read those textbooks, something bothered him. The answers felt vague, too vague. Whenever the question of entanglement arose, the explanations seemed to drift away from clarity. Words like measurement, observation, and information were used generously, but rarely defined. The wave of possibility was said to collapse, but no one could say exactly how or where this collapse occurred, or why it should respect no distance at all. These were not minor gaps. They were cracks running straight through the foundations. What troubled him most was not that the theory was strange, but that its strangeness was treated as unproblematic. The very feature that had once alarmed Einstein, the apparent violation of locality, was now waved away as a philosophical misunderstanding. He did not find that convincing. Rather than accepting the standard story, He began to revisit the original arguments. He read Einstein's objections carefully, not as the complaints of a stubborn old man, but as serious attempts to protect coherence in physics. He noticed how often those objections were summarized rather than addressed, dismissed rather than answered. And he noticed something else. Much of the debate had stalled because it was framed too broadly. Questions were asked in sweeping terms. Is reality local or not? Do particles have properties before measurement or not? These questions invited endless discussion, but no decisive resolution. What if the problem was not the answers, but the questions? This was the quiet shift that changed everything. Instead of asking what quantum mechanics meant, he asked what it assumed. Instead of debating interpretations, he examined the structure underlying them. He wondered whether the comforting idea of locality, the idea that distant events cannot influence one another instantly, could be translated into something precise, something that could be tested. Locality, after all, is not just a feeling. It is a claim about how the world works. If locality is true, then whatever determines the outcome of a measurement here must already be present here. It cannot depend on choices made far away, especially choices made later. The universe, under this assumption, cannot coordinate outcomes across space in real time. This insight was subtle but powerful. Rather than arguing about collapse or hidden variables directly, he focused on the constraints locality would impose on any theory, no matter how clever. If particles really did carry pre-written instructions, then those instructions had to obey certain limits. They could not adapt to last-minute choices. They could not communicate after separation. They could only do what had already been decided. This line of thinking did something remarkable. It stripped the debate of its metaphysical fog. The question was no longer whether quantum mechanics felt uncomfortable, or whether reality seemed strange. The question became much sharper. Can any local explanation, no matter how intricate, reproduce the full pattern of correlations predicted by quantum mechanics? This was not philosophy. It was logic. And logic, unlike interpretation, does not bend easily. What made this approach so striking was its humility. He did not claim to know what the deeper theory should look like. He did not propose new particles or hidden mechanisms. He simply asked what locality itself demanded. If the universe respects locality, then certain patterns must be impossible. If those patterns appear anyway, locality cannot be maintained. This way of thinking transformed the problem completely. The long-standing argument between Einstein and Bohr had often been portrayed as a clash of personalities or philosophies, but now it was being reframed as a question about the universe's behaviour. Not what we prefer, not what feels intuitive, but what nature actually allows. The young physicist worked quietly, without fanfare. His work did not rely on advanced machinery or elaborate experiments. It relied on clarity, on the careful examination of assumptions most people took for granted. When his ideas finally took shape, they did not shout, they whispered. They said simply that if particles carry hidden instructions and if nothing influences anything else faster than light, then the world must obey certain statistical limits. These limits were not arbitrary. They followed directly from the idea that distant regions are independent once separated. And here was the key. Quantum mechanics predicted patterns that brushed up against those limits, and in some cases slipped past them. This realization did not yet tell anyone how the universe worked. It did not declare winners or losers, but it did something far more important. It made the debate testable. For the first time, the question of locality was no longer a matter of taste or temperament. It became a question the universe itself could answer, given the right experiment. The irony was hard to miss. Einstein had long argued that quantum mechanics was incomplete because it violated locality. Bohr had countered that locality was the wrong demand to make. Decades later, a new generation would discover that Einstein's worry was not misplaced, but that the universe did not offer the escape Einstein had hoped for. At this moment in the story, nothing has been decided yet. The patterns have not been measured, the experiments have not been performed. All that exists is a quiet challenge, posed with unusual precision. If the universe truly respects locality, it will behave one way. If it does not, it'll behave another. There is no room left for vague answers. As we drift onward, we'll see how this challenge was put to the test, how particles were asked questions they could not prepare for in advance, and how the universe, when pressed gently but firmly, revealed something astonishing about the way it connects distant events. For now, we can rest with the image of a young physicist sitting with an old discomfort, refusing to dismiss it, and slowly reshaping it into a question sharp enough to pierce the heart of reality. When the question is finally sharpened, it no longer sounds philosophical at all. It sounds practical, almost playful, as if the universe is being invited to a gentle game, one where the rules are simple, and the outcome is decided not by force, but by consistency. Imagine two particles created together, then sent far apart. Each time we examine them, we're allowed to choose how to look, not once, but many times. We can vary our choices freely, even at the last moment, without letting either particle know what the other will face. These choices are like questions asked in different accents. The meaning is similar, but the phrasing changes, and the particles must answer. If the particles carry a pre-written plan, hidden instructions agreed upon when they were together, then that plan must account for every possible question they might be asked. It must tell each particle how to respond no matter which choice is made, and it must do so without any communication after they separate. This is the heart of the test. To make it feel concrete, imagine a simple strategy game. Each particle carries a small script. When asked question A, answer this way. When asked question B, answer that way. The scripts are matched so that when the same question is asked on both sides, the answers fit together perfectly. Balance is preserved. Nothing looks suspicious. So far, so good. Now we complicate the game, but only slightly. Instead of always asking the same question, we allow a few different ones, perhaps 3 options. You can choose any of them at random. The particle does not know which one you will choose until the moment you choose it. This freedom is crucial. The particle's script cannot change, it cannot adapt, it cannot peek across space to see what question was asked elsewhere. All it can do is follow the plan it was given long ago. When this setup is repeated many times, patterns begin to emerge. Sometimes the answers match, sometimes they differ. What matters is not any single outcome, but the overall balance, the frequency of agreement and disagreement across many trials. If the particles are following a local plan, there is a limit to how well they can do. No matter how clever the script, no matter how much foresight it contains, there are combinations of questions where the plan will stumble. The particles will be caught giving answers that disagree more often than they should, or agree more often than they can consistently manage. This is not a matter of skill, it is a matter of constraint. A local plan must commit in advance. It must choose its answers before knowing the questions. And that commitment imposes a ceiling on how coordinated the outcomes can appear. Now here is the remarkable part. Quantum mechanics predict a pattern that gently but decisively crosses that ceiling. The difference is not dramatic. It does not shout, it whispers. In a world governed by local plans, there is a minimum rate at which disagreements must occur when different questions are asked. You can think of it as roughly 1 time in 3. About a third of the time, the answers cannot be made to line up, no matter how clever the preparation. Quantum mechanics predicts fewer disagreements than that. Not 0, just fewer, closer to 1 time in 4. At first glance, this seems trivial, a small difference. The kind of thing that might be dismissed as experimental noise. But this difference is not random. It is systematic. It appears again and again, across different choices, different distances, and different experimental setups. A local plan can approach this pattern, but it cannot reach it. This is why the test is so powerful. It does not rely on perfect coordination. It relies on the inability to do too well. If the particles were allowed to communicate, they could coordinate flawlessly. But communication is forbidden by the speed limit. If the particles are truly independent once separated, then their success rate is capped. Quantum mechanics, by contrast, seems to ignore that cap. Importantly, this does not mean the particles are cheating. They are not sending messages. They are not breaking the speed limit. Each outcome, taken by itself, looks random. No signal can be extracted, no instruction can be sent, and yet, when the results are gathered and compared later, the pattern tells a story that no local script can fully explain. This is why the experiment is sometimes described as one that particles cannot fake. They can fake agreement when asked the same question. They can fake coordination part of the time when asked different questions. But over many trials, the statistics betray them. A local plan leaves fingerprints, and those fingerprints do not match what quantum mechanics predicts. What makes this especially striking is how little machinery is involved. There are no complicated forces at play, no exotic fields, just choices, answers, and careful counting. It is a quiet confrontation. The universe is asked repeatedly whether it can maintain the appearance of locality while still producing the correlations quantum mechanics demands. Each time, it responds the same way. The pattern edges just past what locality would allow, not by much, but enough. This small excess is like a tell in a card game. A tiny habit that gives away a hidden strategy. No single hand proves anything, but over time, the pattern becomes unmistakable. At this point in the story, nothing has been measured yet. We have only predictions. On one side, the calm assurance of locality, insisting that distant things cannot coordinate too perfectly without communication. On the other, the quiet confidence of quantum mechanics, predicting a level of harmony that seems just a little too good to be true. The stage is set. All that remains is to ask the universe directly, to perform the experiments, to count the agreements and disagreements, to see which pattern nature chooses. As we drift onward, the question will finally be answered, not by argument but by observation. And the answer, when it comes, will be both gentle and profound, reshaping our understanding of what it means for distant parts of the universe to be connected at all. For now, we can rest with the idea that sometimes the deepest truths are revealed not by dramatic effects, but by small, persistent differences. Differences that refuse to disappear, no matter how many times the experiment is repeated. Once the question had been sharpened, it could no longer be avoided. The universe had been asked something precise, something it could answer through patterns rather than proclamations. All that remained was to listen carefully. The experiments that followed were not dramatic in appearance. There were no explosions, no blinding flashes, no singular moments where reality seemed to crack open. Instead, there were repeated trials, careful timing, and patient counting. The work required attention, not spectacle. Pairs of particles were created together and then guided apart. One travelled one way, the other travelled another, sometimes separated by meters, sometimes by kilometers. Each particle was met with a measuring device that could be set in different ways, asking different questions about its orientation. Crucially, these choices were made independently. One side did not know what the other would ask. The timing was arranged so that no signal, travelling at or below the speed of light, could coordinate the answers once the particles were on their way. This detail mattered deeply. If locality were truly preserved, then whatever instructions the particles carried had to be enough on their own. Once separated, each particle would be on its own, responding only to its local situation. The experiments were run again and again, the results were recorded, and slowly a picture emerged. When the same question was asked on both sides, the particles behaved exactly as expected. Their answers were perfectly coordinated, preserving the balance they were born with. This was reassuring. It matched both quantum mechanics and any reasonable local explanation. The real test came when different questions were chosen. Here, the patterns mattered more than individual outcomes. One measurement meant nothing by itself. Two meant very little. But thousands, and then millions, of trials began to reveal a rhythm. The frequency of agreement and disagreement followed a clear rule, and that rule matched the quantum prediction, not approximately, not loosely, but consistently. The disagreements occurred slightly less often than any local plan would allow, not by a large margin, but by a margin that refused to shrink, no matter how carefully the experiment was designed. This was not a single result. It was a chorus. Different groups using different methods found the same pattern. Some used light particles, others used different systems entirely. As the years passed, experimental techniques improved, closing loopholes and tightening controls. Each improvement sharpened the question further, and each time the answer remained the same. Nature behaved as though the particles were more closely connected than locality would permit. What made this so striking was not just the agreement with quantum mechanics, but the failure of every local alternative. No matter how the hidden instructions were imagined, no matter how elaborate the planning, the same barrier appeared. Local explanations could get close, but they could not cross the line. Quantum mechanics crossed it gently, without fanfare. It is important to pause here and notice what this does and does not mean. The experiments did not show particles sending messages faster than light. Each measurement, taken by itself, remained unpredictable. There was no way to control the outcome, no way to encode information, no way to send a signal. From the inside of the experiment, nothing felt fast. And yet, when the results were compared afterward, the pattern revealed a coordination that no local story could fully account for. The universe seemed to be stitching distant events together in a way that ignored the usual boundaries of space. This is why the conclusion was so unsettling. It was not that quantum mechanics violated the speed limit. It was that locality itself, our expectation that distant regions behave independently unless connected by signals, could no longer be maintained in its strongest form. The discomfort Einstein had voiced decades earlier had not been resolved. It had been confirmed. But in a way Einstein had not anticipated. He had hoped that the strange features of quantum mechanics pointed toward an incomplete theory, one that could be repaired by adding hidden details. The experiment showed that no such repair could preserve locality. The universe was not merely hiding a classical mechanism behind a probabilistic veil, it was doing something fundamentally different. This realization marked a turning point. For the first time, the tension between quantum mechanics and relativity was no longer a matter of interpretation or taste. It was anchored in experimental fact. The universe itself had answered, and its answer was remarkably consistent. Locality, at least in the way physics had traditionally understood it, could not be upheld. This did not mean that physics collapsed into contradiction. Relativity remained intact in its most crucial role. Causes still preceded effects. Signals still respected the cosmic speed limit. time travel paradoxes remained safely out of reach. But the deeper intuition that distant things are fully independent unless something passes between them had been quietly undermined. The universe, it seemed, was more interconnected than space alone could explain. For many physicists, this was a moment of acceptance rather than shock. The experiments were clear, the predictions were confirmed, there was no escaping the result. The task now was not to argue with nature, but to understand what kind of world could give rise to such behaviour. Some took comfort in the idea that the non-locality revealed by these experiments was subtle, almost ghost-like. It did not carry energy, it did not transmit messages, it did not allow control. It appeared only in correlations, only when results were compared. Others found this unsatisfying. To them, a connection that exists but cannot be used felt like an unfinished explanation. Both reactions were understandable. What mattered most was that the universe had spoken in a clear, steady voice. It had repeated the same answer across decades, across laboratories, across continents. The pattern did not waver. Quantum mechanics was not merely a clever approximation. Its strange predictions reflected something real about the structure of the world. At this point in the journey, the central question shifts again. If the universe allows correlations that defy locality, why does it still refuse to let us exploit them? Why does this faster-than-light-looking influence remain forever out of reach when it comes to sending messages or altering the past? As we continue, we will explore how randomness acts as a kind of safeguard, how the universe permits deep connections while protecting its causal structure, and how, despite appearances, time itself remains safe from contradiction. For now, we can rest with the quiet authority of experiment, not dramatic, not loud, just patient and persistent. The universe answered the question it was asked. And in doing so, it revealed that distance, though still meaningful, is not the final word on how events are connected. By this point in the story, it would be natural to feel a quiet unease. The universe appears to connect distant events in ways that ignore space. Experiments have shown that no local plan can fully explain the patterns we observe. And yet, the most sacred rule of modern physics, the rule that nothing can outrun light, still seems to stand. How can all of this be true at once? The answer lies in a subtle distinction, one that is easy to miss but essential to understanding why the universe does not collapse into paradox. It is the difference between being connected and being able to communicate. To see this clearly, imagine flipping a coin. You toss it into the air and it lands either heads or tails. You cannot control the outcome. No matter how carefully you flick your thumb, the result remains unpredictable. The randomness is genuine. Now imagine that somehow your coin is linked to another coin far away. Each time you flip yours, the other coin also lands, always opposite to yours. If you get heads, the other gets tails. If you get tails, the other gets heads. This is already strange. But notice what you still cannot do. You cannot choose to send heads or tails as a message. You cannot decide what the distant observer will see. All you can do is flip your coin and accept the result. The correlation is perfect, but control is absent. This is the essential structure of quantum entanglement. Each measurement produces a random outcome. There is no dial to turn, no switch to flip, no setting that lets you decide the result. From the perspective of someone performing the measurement, the universe answers with a shrug, sometimes one way, sometimes the other. Because of this randomness, entanglement cannot be used to send information. There is no way to encode a message in outcomes you cannot control. Even though the distant particle's result is perfectly correlated with yours, that correlation only becomes meaningful after the fact, when results are compared. And that comparison requires a normal, slower-than-light channel. This is why the experiments do not allow time travel tricks. Imagine trying to send a message to the past using entangled particles. You perform a measurement now hoping to influence a distant event earlier in time, but your measurement yields a random result. You have no way of shaping what happens. The universe refuses to cooperate. From the inside of the experiment, everything feels ordinary. You make a choice about how to measure. You observe an outcome. It looks like chance. Only later, when results from both sides are brought together, does the deeper pattern emerge. The correlations appear in the comparison, not in the individual events. This is sometimes described as nature allowing correlation without communication. It is delicate compromise. The universe permits connections that ignore distance, but it denies us the ability to use those connections as tools. Influence seems to be present, but agency is not. Something links the outcomes, but nothing lets us steer them. This structure is not an accident. It is what keeps causality intact. If outcomes were not random, if you could choose them, then the door to paradox would swing open. You could send signals faster than light. Different observers could disagree not just about timing, but about what caused what. The universe's story would fracture. Randomness closes that door. In a sense, randomness acts like a protective veil. It allows the universe to be deeply interconnected while preventing those connections from being exploited. The patterns exist, but they are inaccessible until all relevant information is gathered in one place. This is why, despite appearances, nothing truly outruns light in the operational sense. No message arrives before it is sent. No effect can be used to cause itself. The faster-than-light-looking influence remains subtle, statistical, and untouchable. This is also why the experiments feel so unsatisfying to those who want a mechanical explanation. There is no lever to pull. No signal to trace. The connection reveals itself only when we step back and look at the whole. It is as if the universe whispers its secrets in the margins, never in the main text. For many physicists, this compromise is acceptable. It preserves the practical rules needed to do science and build technology. Computers work, satellites synchronize, causes still precede effects in every usable sense, and yet, the deeper discomfort does not vanish. Even if we cannot use entanglement to send messages, the fact remains that distant outcomes are linked in a way that ignores space. The universe seems to coordinate itself behind the scenes, even if it refuses to let us participate in that coordination. This raises a subtle but important point. Relativity tells us how signals behave. It tells us what can be used to transmit information and energy. It does not by itself tell us how correlations must behave. Quantum mechanics exploits this gap. By hiding its non-locality inside randomness, the universe satisfies the letter of relativity while bending its spirit. Nothing observable travels faster than light, but something deeper seems to tie distant events together without delay. This is why the situation is often described as an uneasy truce. Neither theory fully conquers the other. Relativity keeps its speed limit. Quantum mechanics keeps its correlations. They coexist, but not comfortably. For now, though, the universe remains safe from contradiction. You cannot build a faster-than-light telephone. You cannot warn the past. You cannot change yesterday by measuring today. The structure holds. And perhaps that is the most remarkable part of all. The universe allows itself to be strange without allowing itself to break. It permits deep connections, but it fences them in with uncertainty. As we drift forward, we will look more closely at this uneasy balance. We will see how different observers can tell different stories about the same quantum events, and why those stories, though unsettling, never quite tear the fabric of time. For now, you can rest with the reassurance that even in a universe where distance is not the final word, causality remains gently protected, guarded not by speed alone, but by the quiet unpredictability at the heart of quantum reality. Even after accepting that entanglement cannot be used to send messages or cheat time, a quiet tension remains. It lingers not in what we can do, but in how the universe seems to arrange itself behind the scenes. The rules of relativity still stand firm in practice, yet quantum mechanics appears to lean against them in an uncomfortable way. To feel this tension, it helps to return to a simple idea: the order of events. In everyday life, the order of events feels absolute. One thing happens, then another. Cause comes before effect. This sequence feels so basic that we rarely question it. But relativity taught us something unsettling: that the order of distant events can depend on how you move. Two events that appear simultaneous to one observer may occur in different orders for another observer moving at a different speed. Neither observer is wrong. Time itself adjusts to motion. Normally, this flexibility causes no trouble, as long as signals respect the universal speed limit. All observers still agree on which events can influence which others. Causes remain causes, effects remain effects. Quantum mechanics complicates this picture. Consider two entangled particles measured far apart. One observer might describe the situation by saying that the measurement here caused the outcome there. Another observer, moving differently, might insist that the distant measurement happened first and influenced the local result. A third observer could see the two measurements as happening at the same time, with no clear sense of which came first. All three descriptions are allowed, and yet the correlations between the outcomes remain exactly the same in every case. This is where the discomfort sets in. If you try to tell a single, global story about what caused what, you quickly run into trouble. The universe seems unwilling to commit to a unique narrative. Instead, it offers a set of consistent outcomes without specifying a single chain of influence that all observers must agree on. Relativity tells us how clocks behave. Quantum mechanics tells us how correlations behave. Together, they refuse to provide a simple picture of causation at a distance. This does not mean that physics is inconsistent. The predictions are clear. The experiments work. No contradictions arise. But the underlying story feels incomplete, as if an important chapter has been written in a language we do not yet fully understand. One way to think about this is to distinguish between two kinds of rules. There are operational rules, the ones that govern what we can measure, control, and use. These rules are strict and well-behaved. They tell us that signals cannot outrun light, that messages cannot arrive before they are sent, and that experiments produce consistent results. Then there are structural rules, the ones that describe how reality is stitched together beneath those measurements. These rules are more elusive. They concern how events relate to one another when no single observer's perspective is privileged. Quantum mechanics seems to bend these structural rules without breaking the operational ones. From the standpoint of any given observer, nothing illegal occurs. Each measurement looks local. Each outcome appears random. Each experiment respects the speed limit. But when all perspectives are considered together, the correlation suggests a deeper level of connection that does not fit neatly into a space-time picture built entirely from local influences. This is why the situation is often described as a truce rather than a victory. Relativity has not been overthrown. Its core principles remain intact where it matters most. Quantum mechanics, meanwhile, has not been forced into a local mould. Its non-local correlations persist, confirmed again and again by experiment. The two theories coexist, but they do so with a sense of mutual restraint. Relativity says, you may not send signals faster than light. Quantum mechanics replies, I will not let you control outcomes. Together they form a kind of balance. This balance is stable, but it is not satisfying. For those who care deeply about understanding rather than mere prediction, the lack of a clear causal story feels like an unfinished thought. The universe behaves as if distance matters less than we expect, yet it refuses to explain how this can be reconciled with the structure of space and time. Some physicists view this as a temporary state of affairs. They suspect that a deeper theory, one that unites quantum mechanics and relativity, will eventually reveal a clearer picture. Perhaps space-time itself will turn out to be emergent, not fundamental. Perhaps locality will need to be redefined rather than abandoned. Others are more cautious. They note that every attempt to force quantum mechanics into a familiar causal framework has met resistance. The universe seems remarkably comfortable with ambiguity, even if we are not. What is important, especially in the context of this story, is that the tension never escalates into contradiction. No experiment has ever produced a result that violates the practical rules of causality. No observer has ever witnessed an effect that could be used to rewrite the past. The discomfort remains philosophical, not operational. This is both reassuring and frustrating. Reassuring because it means the universe remains navigable. Frustrating because it means the deeper questions remain unanswered. In a sense, quantum mechanics invites us to loosen our grip on certain intuitions. It suggests that insisting on a single, observer-independent account of distant causation may be asking too much. The world may not be obligated to tell its story in the way we find most comfortable, and yet the desire for such a story persists. As we move forward, we will see how different interpretations of quantum mechanics attempt to resolve this tension in different ways. Some accept non-locality openly, others remove collapse altogether. Each choice preserves certain intuitions while sacrificing others. For now, we can sit with the idea that physics has reached a point where consistency no longer guarantees clarity. The universe works, it follows its rules. But those rules, when viewed together, hint at a structure deeper and stranger than space-time alone. This uneasy truce is not a failure. It is a sign that we've reached the edge of what our current theories can comfortably explain. Beyond that edge lies a question still waiting for its answer, and as with many deep questions in physics, the universe does not rush. It allows us to live with the tension, to explore it gently, and to accept that understanding sometimes unfolds more slowly than discovery. Even after accepting that entanglement cannot be used to send messages or cheat time, a quiet tension remains. It lingers not in what we can do, but in how the universe seems to arrange itself behind the scenes. The rules of relativity still stand firm in practice, yet quantum mechanics appears to lean against them in an uncomfortable way. To feel this tension, it helps to return to a simple idea: the order of events. In everyday life, the order of events feels absolute. One thing happens, then another. Cause comes before effect. This sequence feels so basic that we rarely question it. But relativity taught us something unsettling: that the order of distant events can depend on how you move. Two events that appear simultaneous to one observer may occur in different orders for another observer moving at a different speed. Neither observer is wrong. Time itself adjusts to motion. Normally, this flexibility causes no trouble. As long as signals respect the universal speed limit, all observers still agree on which events can influence which others. Causes remain causes, effects remain effects. Quantum mechanics complicates this picture. Consider two entangled particles measured far apart. One observer might describe the situation by saying that the measurement here caused the outcome there. Another observer, moving differently, might insist that the distant measurement happened first and influenced the local result. A third observer could see the two measurements as happening at the same time, with no clear sense of which came first. All three descriptions are allowed, and yet the correlations between the outcomes remain exactly the same in every case. This is where the discomfort sets in. If you try to tell a single global story about what caused what, you quickly run into trouble. The universe seems unwilling to commit to a unique narrative. Instead, it offers a set of consistent outcomes without specifying a single chain of influence that all observers must agree on. Relativity tells us how clocks behave. Quantum mechanics tells us how correlations behave. Together, they refuse to provide a simple picture of causation at distance. This does not mean that physics is inconsistent. The predictions are clear. The experiments work. No contradictions arise. But the underlying story feels incomplete, as if an important chapter has been written in a language we do not yet fully understand. One way to think about this is to distinguish between two kinds of rules. There are operational rules, the ones that govern what we can measure, control, and use. These rules are strict and well behaved. They tell us that signals cannot outrun light, that messages cannot arrive before they are sent, and that experiments produce consistent results. Then there are structural rules, the ones that describe how reality is stitched together beneath those measurements. These rules are more elusive. They concern how events relate to one another, when no single observer's perspective is privileged. Quantum mechanics seems to bend these structural rules without breaking the operational ones. From the standpoint of any given observer, nothing illegal occurs. Each measurement looks local. Each outcome appears random. Each experiment respects the speed limit. But when all perspectives are considered together, the correlations suggest a deeper level of connection that does not fit neatly into a space-time picture built entirely from local influences. This is why the situation is often described as a truce rather than a victory. Relativity has not been overthrown. Its core principles remain intact where it matters most. Quantum mechanics, meanwhile, has not been forced into a local mould. Its non-local correlations persist, confirmed again and again by experiment. The two theories coexist, but they do so with a sense of mutual restraint. Relativity says, you may not send signals faster than light. Quantum mechanics replies, I will not let you control outcomes. Together they form a kind of balance. This balance is stable, but it is not satisfying. For those who care deeply about understanding rather than mere prediction, the lack of a clear causal story feels like an unfinished thought. The universe behaves as if distance matters less than we expect, yet it refuses to explain how this can be reconciled with the structure of space and time. Some physicists view this as a temporary state of affairs. They suspect that a deeper theory, one that unites quantum mechanics and relativity, will eventually reveal a clearer picture. Perhaps space-time itself will turn out to be emergent, not fundamental. Perhaps locality will need to be redefined rather than abandoned. Others are more cautious. They note that every attempt to force quantum mechanics into a familiar causal framework has met resistance. The universe seems remarkably comfortable with ambiguity, even if we are not. What is important, especially in the context of this story, is that the tension never escalates into contradiction. No experiment has ever produced a result that violates the practical rules of causality. No observer has ever witnessed an effect that could be used to rewrite the past. The discomfort remains philosophical, not operational. This is both reassuring and frustrating. Reassuring, because it means the universe remains navigable. Frustrating, because it means the deeper questions remain unanswered. In a sense, quantum mechanics invites us to loosen our grip on certain intuitions. It suggests that insisting on a single, observer-independent account of distant causation may be asking too much. The world may not be obligated to tell its story in the way we find most comfortable, and yet, the desire for such a story persists. As we move forward, we will see how different interpretations of quantum mechanics attempt to resolve this tension in different ways. Some accept non-locality openly, others remove collapse altogether. Each choice preserves certain intuitions while sacrificing others. For now, we can sit with the idea that physics has reached a point where consistency no longer guarantees clarity. The universe works. It follows its rules. But those rules, when viewed together, hint at a structure deeper and stranger than space-time alone. This uneasy truce is not a failure. It is a sign that we have reached the edge of what our current theories can comfortably explain. Beyond that edge lies a question still waiting for its answer. And as with many deep questions in physics, the universe does not rush. It allows us to live with the tension, to explore it gently, and to accept that understanding sometimes unfolds more slowly than discovery. After the experiment spoke so clearly, the universe left us with a choice. Not a technical one, but a philosophical one. If locality could not be fully preserved, then something else had to give way. The question was not what the equations predicted, they were already precise, but how we should understand what those predictions meant. One response, which had guided physics for much of the 20th century, was surprisingly modest. It did not attempt to explain everything. It didn't insist on a picture of what reality was doing behind the scenes. Instead, it chose restraint. This response came to be known as the Copenhagen view, though it was never a single, rigid doctrine. It was more like an attitude, a way of deciding which questions physics should answer, and which questions it should quietly set aside. At its heart was a simple move. Quantum mechanics, according to this view, is a tool for predicting the outcomes of measurements. It does not describe an underlying reality independent of those measurements. Asking what a particle really is before it is measured is considered an unproductive question, not because it is meaningless in a philosophical sense, but because the theory offers no answer to it. When a measurement occurs, the wave of possibilities collapses to a single outcome. That collapse is not described as a physical process travelling through space. It is simply the update of what can be said meaningfully about the system. This move is subtle, and it is easy to misunderstand. The Copenhagen approach does not deny the experimental facts. It accepts them fully. It accepts that entangled particles display correlations that ignore distance. It accepts that these correlations cannot be explained by any local hidden plan. What it refuses to do is tell a detailed story about how those correlations come to be. In this view, asking whether the collapse happens here first or there first is already a mistake. The collapse is not an event in space-time like a ripple or a signal. It is a change in description, not a physical influence moving from one place to another. This is how Copenhagen lives with non-locality. It does not celebrate it. It does not deny it. It simply refuses to treat it as a physical mechanism in need of explanation. To many physicists, this restraint was a relief. The equations worked. The predictions were accurate. Technologies built on quantum principles functioned reliably. By declining to speculate about what lay beneath the formalism, physics could move forward without becoming entangled in metaphysical debates. In practice, this approach proved enormously successful. Lasers, transistors, magnetic resonance imaging, and much of modern electronics rely on quantum mechanics. Engineers did not need a detailed story about collapse to make these devices work. They needed reliable calculations, and quantum mechanics provided them. From this practical standpoint, Copenhagen felt like wisdom. It recognized the limits of what could be said and chose not to cross them. It treated the measurement process as fundamental, even if mysterious, and accepted that the theory might be complete in its own way, even if it left deeper questions unanswered. But this success came at a cost. By refusing to describe what happens between measurements, Copenhagen left a conceptual gap at the heart of physics. The world seemed to flicker between potential and actuality, with no account of how or why. The role of the observer, though often softened or reinterpreted, never entirely disappeared. For some, this was tolerable. For others, it felt like surrender. The discomfort was not that Copenhagen was wrong. It was that it felt unfinished. Physics, after all, had a long tradition of pushing past appearances to uncover deeper structures. Declaring certain questions off limits felt like an abandonment of that tradition, and yet it was hard to argue with results. Whenever physicists tried to go beyond Copenhagen by adding hidden details while preserving locality, they ran into Bell's wall. Whenever they tried to describe collapse as a physical signal, they risked violating relativity. The Copenhagen stance avoided these pitfalls by stepping aside. It accepted the world as it appeared in experiments and declined to say more. In doing so, it preserved a kind of peace between quantum mechanics and relativity. The peace was uneasy, but it held. No contradictions arose. No paradoxes escaped the laboratory. Physics remained internally consistent and externally successful. This is why Copenhagen endured. It was not because it was deeply satisfying, it was because it was deeply useful. In a way, Copenhagen treats quantum mechanics as a map rather than a mirror. The map tells you where you can go and what you can expect to see. It does not claim to reproduce every detail of the terrain beneath your feet. As long as the map works, you can travel safely, but some travellers are not content with maps alone. They want to know what the land is really like, even in places no one has yet walked. For them, Copenhagen's refusal to speak feels like a silence that demands to be broken. And so, alongside this pragmatic acceptance, other interpretations continued to grow. Some embraced non-locality openly. Others chose a more radical path, removing collapse entirely and reshaping the notion of reality itself. As we continue, we will explore one of those paths, a path that avoids instantaneous collapse not by explaining it, but by denying that it ever happens at all. For now, we can rest with the Copenhagen choice. It asks us to focus on what can be said, measured, and predicted, and to let go, at least temporarily, of the desire for a complete picture of reality. It is a position of discipline rather than defeat. Whether that discipline is wisdom or limitation remains an open question. As the story comes to rest, it circles back to where it began, not to close the loop, but to sit quietly inside it. Einstein's worry was never a rejection of quantum mechanics' success. He admired its power, he used it, he helped build it. What troubled him was something deeper and more personal. A sense that the theory, for all its accuracy, left the world oddly fragmented, as if distant parts of reality were being stitched together without thread or needle. For a long time, it was tempting to think this worry would eventually dissolve, that clearer experiments or better mathematics would show the discomfort to be an illusion, that locality would be restored, or that the strange correlations would fade under closer inspection. Bell changed that expectation forever. He did not prove Einstein wrong in the way many summaries suggest. He proved something subtler and far more unsettling. He showed that Einstein's concern was not philosophical hand-wringing. It was a precise intuition about the structure of the world. Locality, understood as the idea that distant things are fully independent unless something passes between them, really does fail. The universe itself says so. But Bell also showed that the escape Einstein hoped for, a deeper local explanation hiding beneath quantum mechanics, does not exist. There is no simple repair, no missing gear, no classical story waiting patiently to be uncovered. This leaves us in a curious position. Einstein was right to worry. He was wrong about how that worry could be resolved. The experiments did not restore the world he hoped for, but they also did not plunge physics into chaos. Instead, they revealed a universe that is orderly, consistent, and deeply strange, one that respects its rules while quietly undermining our intuitions. In this universe, distance is real, but not absolute. Time is ordered, but not universal. Outcomes are definite, but only from within a given story. Whether we choose to live with collapse, or to accept many branching outcomes, or to embrace some other interpretation still being developed, the lesson is the same. Certain combinations of beliefs cannot all be held at once. Something familiar must be surrendered. This is not a failure of physics. It is a sign of maturity. Every major shift in our understanding of nature has demanded a similar sacrifice. The Earth lost its central place. Absolute time dissolved. Space became flexible. Each time, the universe grew larger and less intuitive, but also more coherent. Quantum mechanics continues that tradition. What remains unresolved is not the data, but the meaning. The equations work, the experiments agree, technologies flourish, and yet the question of how reality knits itself together across space and time remains unanswered. Perhaps this is why the unification of quantum mechanics and gravity has proven so difficult. The failure to reconcile these theories may not be due to a lack of cleverness or computation. It may reflect a deeper mismatch between our inherited concepts and the world they are meant to describe. Locality, causality, and reality itself may need to be rethought, not patched, and so the universe whispers rather than declares. It shows us patterns that cannot be faked. It allows connections we cannot use. It respects limits without explaining why those limits are enough. In the end, Bell did not tell us what the universe is. He told us what it cannot be, and that narrowing of possibility is itself a kind of progress. We are left not with certainty, but with clarity about the shape of our ignorance. This is a gentle place to stop, not with a final answer, but with an invitation to rest inside the question. To accept that understanding does not always arrive as a solution, but sometimes as a deeper appreciation of mystery. The universe continues to work quietly and reliably, even when it refuses to explain itself fully. And perhaps that too is a kind of lesson. You do not need to resolve these ideas tonight. You do not need to choose an interpretation or defend a position. It is enough to know that the worry was real, the answer was surprising, and the story is still unfolding. As your thoughts begin to slow, you can let them drift alongside this unfinished understanding, like light travelling through space carrying information but not urgency. The universe is not in a hurry, and neither are you.